Gibson here. Today we're going to move on and look at Newton's third law of motion. So the objectives for today will be able to define what Newton's third law says, explain the concept of the interaction of force pairs. It's the central idea around Newton's third law of motion, and then be able to give examples of Newton's third law and the implications of it. So let's do a quick review. Newton's first law of motion, right, says that an object that is at rest remains at rest. An object in motion will remain in motion if the net force on that object is zero. Or another way to say that is objects keep on doing what they're doing unless acted upon by a net force. Sometimes also we refer to this as the law of inertia. Newton's second law gives us the relationship between acceleration, net force, and mass. So the acceleration is directly proportional to the force and inversely proportional to the mass. The direction of the acceleration is always in the same direction of the force, and the units for force are a Newton. So now that brings us to Newton's third law of motion. And it says, for every action, there is an equal and opposite reaction. This may be the most well-known of the three laws of motion. But what does it really mean? So let's look at this picture here. What's happening? Well, most people would say that the hammer is hitting the nail. So clearly, we have a force that the hammer is exerting on the nail. But Newton's third law says that for every action, there is an equal and opposite reaction. So there must be a reaction force. Besides the hammer hitting the nail is hitting or pushing back on the hammer. So when we identify these action and reaction force pairs, there's some rules that we're going to abide by to be able to identify and define them. The first is the forces must always be equal in magnitude. So the force of the hammer hitting the nail is equal to the force of the nail pushing back on the hammer. The forces are always in the opposite direction. And the forces always come in pairs. There has to be two forces, a pair of what we call action-reaction pairs. And then the last part, when you're defining these, is the action-reaction pair never acts on the same object. In other words, notice that the hammer acts on the nail, but then the nail, it doesn't act on itself, it reacts back to the hammer. So let's look at some examples here, see if we can identify the action and the reaction force. So we'll start with an example we've looked at many times now in this unit, a book sitting on a table. So what would the action force be? Well, we have gravity pushing down on the book, which pushes down on the table. So we could say book pushing down on table is the action force, and the reaction force would be the table pushing up on the book, or sometimes what we call the normal force. Let's try another one here. So what would the action force be? Well, the primary one, right, is the bat hitting the ball. But the ball actually hits the bat. That is the reaction force to it. This one maybe looks a little uncomfortable. So see if you can identify the action-reaction force. All right, so the boxing glove is hitting the face, but the face is actually pushing back on the glove. So here's one that's kind of interesting, right? We've got potential for a couple different forces here. The action-reaction force. The first is the hot gas pushing the bullet, right? That's what actually causes the bullet to accelerate down the gun barrel and fly out. The hot gas pushing inside. When you pull the trigger, it explodes the gunpowder and creates that hot gas. The reaction force is actually the bullet pushing back on the hot gas. There's another force. The hot gas not only pushes the bullet forward, but it pushes the gun backwards. And if you've ever fired a gun or a rifle, you've experienced this before, right? We call it recoil. And so the gun has to be pushing back on the hot gas. If you're not holding that gun very firmly in your hand and ready for it, the gun will fly back and hit you right in the face or the chest. We call that the recoil force. Here's another one. So this is a space shuttle, right? Hasn't flown in many years. We now are flying again, thanks to SpaceX. But what's the action and reaction force? So the rocket, right, is pushing out the hot gas. So that's the whole purpose of a rocket engine or a jet engine, right? Is to create this high pressure stream or flow of hot gas pushing out of the nozzle in this case. And the reaction force is the hot gas pushing back on the rocket. Now, you may ask yourself, what actually causes a rocket to accelerate, to lift off and fly into space? And most people would say, oh, it's the flames or the hot gas coming out. But it's actually the hot gas pushing back on the rocket. And you may think, well, how can just gas, something, like a superheated gas, be able to lift a huge rocket? Well, there is tremendous pressure in that gas right at the nozzle, and it has the ability to push an equal and opposite force back on the rocket and actually cause it to lift and accelerate. All right, one more here. See if you can identify, right, the force pairs. And there's quite a few here. See if you can find at least 3, maybe pairs of action and reaction forces. Okay, let's step through them. So first, we have the man on the right pulling on the rope. And so the rope pulls back on the man. And we could say the same thing on the other side. The man on the left pulls on the rope, and the rope pulls on the man on the left to the other direction, to the right. They've got their foot on the ground, right? So the foot is pushing on the ground. What's the ground going to do? Push back on the foot. And then we could do the same thing on the other side. Now, you may be able to identify more pairs besides kind of the horizontal pushing, the frictional force of the foot on the ground. There is also the gravitational and normal force, right? That will almost be a action-reaction force pair in every situation where you have something resting on a flat surface. All right, now we understand that there'll always be an action and reaction forces, right, in any situation. But let's take it the next step here, right? If they have equal and opposite forces acting on the two objects that are interacting, why don't they behave the same way? Well, this is where Newton's second law comes into play with Newton's third law. So what are the two objects here, right? Cannon. So the cannonball, let's look at that one more time here. Fired the cannonball. Now notice the cannon flies, or the cannonball flies rapidly to the left. The cannon itself moved slowly to the right a little bit. So why do they have different motion, different acceleration, if they are both experiencing the exact magnitude of the force, the cannon on the cannonball and the cannonball back on the cannon? Well, here's the two action forces, right? But the difference, of course, is their mass. Right? The cannon itself has a much heavier mass than the cannonball. So when it experiences the same force, it's going to have a much lower acceleration. Think of Newton's second law, right? It's inversely proportional to the mass, so lower acceleration. The cannonball, right, is going to accelerate at a much higher rate because it has a lower mass. So if they experience the same force, but the cannonball is only 1/100th of the mass of the cannon, then it's going to experience an acceleration that's 100 times greater than what the cannon is. And that's why they build cannons so big and heavy. Let's see if this little video here will play. Now, you may snicker, that is painful. But that's one of the first things they're taught in the military, right? When you're learning to fire artillery or a cannon, is don't stand behind it when you launch it. Let's watch it one more time. So hopefully he wasn't injured too greatly there. All right, let's look at another example of this action and reaction. Let's say that I jump up and down on the surface of the earth. Now, when I push up to jump up into the air, I'm applying a force. The reaction force, right, is that the earth has to push back up on me, okay? So if the earth and I both experience the exact same force, why do I jump up and the earth, at least from our perspective, appears to be stationary, that does not move? Okay? It remains at rest. Well, it goes right back to the mass. The mass of the earth is about 6 times 10 to the 24th. So imagine 6 with 24 zeros after it, kilograms, right? The mass of a person is about 60 kilograms, okay? So you could say 10 to the 23rd power, right? More mass on the earth than a person has. So obviously, when I push off, I'm going to have an acceleration much, much, much greater than that of the earth. Now, since their accelerations are inversely proportional to the mass, if I jump up, right, and push up, and it caused me to accelerate 1 meter per second upwards, then how much acceleration would the earth actually experience? So we could never measure it, we could never feel it, but when I jump up off the surface of the earth, I am causing the earth to accelerate a very, very, very tiny amount back in the opposite direction. How much would it be? Well, it would be 1 divided by 10 to the 23rd. So I won't even try to describe what that number is actually, but extremely, extremely small, right? So we accelerate upward, the earth accelerates downward, but it's so small, we can calculate it, but it's really not measurable. We certainly wouldn't feel it. Now, what if we had all 6 billion people on Earth come together in one place and we all jumped at exactly the same time? Could we cause the Earth to accelerate to the point where we would notice it or actually change the position of Earth a little bit? Well, even if we had all 6 billion people, I guess it's closer to 7 billion now, you can see that the acceleration on Earth would still be extremely small, not noticeable, and certainly not measurable. All right, let's watch a short little video now that does a good job of explaining early in the days of spaceflight. All the scientists and engineers that working on the program had forgotten about Newton's third law of motion when they began to ask the astronauts to do work in space.
On March 18, 1965, Russian cosmonaut Alexei Leonov became the first human to float in space. Not to be outdone, the United States sent astronaut Ed White into outer space just 3 months later.
You're right in front, Ed. You look beautiful. I feel like $1 million.
He floated for 20 minutes and loved every bit of it. Floating around is fun and easy, but the next American would have to do more than just float. Gene Cernan would try to find out if humans could do work in outer space.
I was going to go out and I was going to have to do legitimate work. I had to basically assemble a whole flying backpack outside the spacecraft in zero gravity through a nighttime cycle where I had little or no light.
Cernan was supplied oxygen from an umbilical hose that passed through an open hatch. His commander, Tom Stafford, seated inside, piloted the spacecraft. Cernan quickly discovered that handling even simple objects was extremely difficult.
And every time I'd push or turn a valve, it would turn my entire body in zero gravity. I had nothing to hold on to. And we take for granted gravity because we can do that kind of work with ease if something is holding our feet to the ground. Nothing was holding me anywhere.
Within minutes, Cernan was sweating from the extreme effort it took to control his movements.
Within a few minutes, he fogged over. We were so naive, we didn't even think about putting defog on our visor like you do when you go snorkeling or scuba diving. And so he was huffing and puffing, and I was flying the spacecraft. He says, "Tom, I've got a hard time controlling myself."
And it was a very, in retrospect, somewhat of a hair-raising thing. And there were probably times where there were people down here on Earth wondered whether I'd get back in because my heart rate was running at 170 beats a minute.
I said, "Hey, this is not a good situation at all." So I called the ground and the contact said, "I've called it quits. I'm going to get him back in before we go into the next nighttime." Got him in. Finally, he just couldn't hardly move. And then when he opened his visor, he was absolutely pink, like he'd been in a sauna about an hour too long. The next day we landed and they flew the suit right back to Houston. They had over a pound or a pound and a half of water out of each boot. But he lost, I think, 10 and a half pounds in 2 hours and 5 minutes outside.
NASA was now determined to find out what went wrong.
As engineers, we started saying, look, we've had 3 missions where the EVAs didn't go well. What was wrong? Then we had a science advisory team step in and say, look, your entire principles of EVA are wrong. How you train, how you prepare the crew.
Everybody forgot Newton's third law of motion. To every action, there's an opposite and equal reaction. And when they touched the spacecraft repelled them.
Although weight is reduced in outer space, the mass of an object is unchanged. To move a mass, force must be applied. Newton's third law predicts an equal but opposite reaction. On Earth, gravity would allow Cernan to gain a footing and counteract the reactive force. But in outer space, the reactive force sent him reeling. Having learned a difficult lesson, NASA's next capsule was built with special handholds and footholds to anchor the astronaut in place. Most importantly, NASA began training astronauts underwater, the closest environment on Earth to weightlessness. The new training and tools made a big difference for Buzz Aldrin, the next American astronaut to do work in outer space.
I felt that it was a piece of cake outside, just moving very slowly. There was no challenge. You decide that you're going to move in a certain way and you need leverage, so you just don't allow yourself to get out of position.
All right, so we know how to define Newton's third law. We know how to explain how we identify these force pairs and the interaction between them. And we can come up with examples. And hopefully, as you work on your Newton projects, you will be able to come up with some good examples of your own. All right, that's it for today. Thanks.